Today, we're digging into a really cool paradox that sits right at the heart of modern AI. It turns out the very same thing that makes these large language models so smart is also what makes them feel, well, kind of slow. It's the engine, and it's also the bottleneck.
You know the feeling, right? You ask your favorite chatbot a question, and then you watch as it spits out the answer word by word. Why does it do that? Why can't it just give you the whole thing at once? Well, to get to the bottom of that, we have to understand the one fundamental idea that powers pretty much all of them. And the answer is a concept called autoregression. Now, I know, it sounds a little technical. It comes from the world of statistics. But it's actually a pretty simple and really powerful idea that has become the absolute backbone of the generative AI we all use every single day. At its core, it's a beautifully simple concept. Auto means self, and regression is just a fancy word for predicting something. So autoregression is just self-prediction. To figure out what's coming next, you just look at what already happened. Simple as that. Think about it this way. If I say to you, to predict the next word, you need to know the words that came, instinctively that the next word is before, right? You couldn't have known that without hearing the first part of the sentence. And that right there is autoregression in action. The past predicts the future. Now, this isn't some brand new idea that was just invented for chatbots. Nope. Autoregression has been a workhorse in data science for decades. So let's take a quick look at how this idea evolved. Way back in the 1950s, economists were using it to forecast market trends, and meteorologists were using it to predict the weather. They were using past data to guess the future. Then it got picked up for things like audio signal processing. By the 2010s, it became the key ingredient for getting machines to understand and generate language. And today, it is everywhere, from the text you get from ChatGPT to the voices you hear from models like Volley. And here's the more formal, mathy way of saying the exact same thing. But don't worry about the jargon. A realization at time t, that's just the next word. And a linear combination of the previous realizations, that's just a fancy way of saying the model looks at all the previous words, weighs how important each one is, and uses that information to make its best guess for the next one. It's a very careful, step-by-step process. But, and this is the big but, that methodical, step-by-step process has a major downside. Being so careful is precisely what creates the bottleneck that leaves us waiting for our answers. So let's break down exactly what the AI is doing. First, it generates just one single piece of a word, a token. Then, and this is the most important part, it has to take that new token and add it back into the sequence it's thinking about. Only then can it generate the next token. It's this constant loop. Generate, feedback, over and over and over again for every single word. And that is the whole problem. It's a sequential dependency. The model literally cannot generate word number 5 until it has successfully generated word number 4. It's like building a tower of Legos. You have to place one brick at a time in order. You can't just throw them all up in the air and have them land perfectly stacked. That's why it's slow. Now, there's another little complication here called exposure bias. See, when these models are being trained, they use a trick called teacher forcing. At every step, they're shown the correct next word. It's kind of like training with the answer key. But out here in the real world, when we're using it, there is no answer key. The model has to rely on its own words that it just generated, which, might not be perfect. The big fear has always been that one little mistake could cause a cascade of errors and send it completely off the rails. But here's a really fascinating twist. Recent studies are finding that these models are surprisingly tough. They seem to have what's called a self-recovery ability. Even if you feed them a slightly weird or incorrect history, they often manage to get right back on track. In fact, some research suggests this whole exposure bias thing might only cause a tiny performance drop, maybe only 2 or 3%. So while it's a real thing, it might not be the catastrophic problem people once thought it was. Okay, so if the big bottleneck is this one word at a time process, the billion-dollar question for researchers is, how do we break it? This has kicked off an incredible race to find clever ways to speed up AI generation without wrecking the quality. And this brings us to two main philosophies. On one hand, you have autoregressive, or AR, which we've been talking about. It's slow, but it produces really high-quality, coherent text. The alternative is non-autoregressive, or NAR. This approach tries to generate all the words in parallel, all at once. It's blazing fast, but the quality can often take a nosedive because it loses that crucial step-by-step context. So one of the most popular tricks to get the best of both worlds is something called speculative decoding. And the idea is just brilliant. You use a small, fast model to quickly generate a draft of the next few words. Then, the big, powerful, and slow model looks at that draft and, in one single parallel step, just verifies if it's correct. It's so much faster for the big model to check someone else's work than to do it all from scratch. And now, we're seeing the next evolution of that idea: speculative streaming. Instead of using two different models, this uses a super clever trick called multi-stream attention. It basically lets a single model do two things at once. While it's confirming the very next word, it's already predicting several possible future words further down the road. It's like a chess master thinking several moves ahead. The results are amazing, a 2 to 3.5 times speed up, and it's incredibly efficient. Now check out this graph. It shows that planning ahead in action. Just focus on those blue and orange lines. As you move from left to right, going deeper into the model's layers, you can see those lines are climbing higher and higher. That means the model's predictions about the future are getting more and more accurate as it processes the information, perfectly aligning its guesses with the right answer. All right, let's look at one final technique, which takes a different but equally clever approach. The goal here is simple: train those super fast NAR models to have the same high quality as their slow AR cousins. The concept is called knowledge distillation, and honestly, the analogy is perfect. You take a huge, expert AR model, that's the teacher. It produces fantastic results, but slowly. Then you use its high-quality answers to train a much smaller, faster NAR model, that's the student. The student literally learns to mimic the teacher's great decisions, but because it's an NAR model, it can make them all at once, in parallel. And the impact here is massive. By using this knowledge distillation method, researchers have been able to get speeds that are 4 to 5 times faster than the original high-quality autoregressive models they learned from. And this table shows you the hard numbers from a study that used this technique. Just look at the times. The AR teacher model took 0.422 seconds. Its NAR student model, just 0.043 seconds. Now look at the optimality gap column. That's the quality score. There's almost no drop in performance at all. The result? The student is just as smart as the teacher, but it's nearly 10 times faster. Incredible. So we come all the way back to this core tension. Autoregression gives us that precision, that coherence that we want, but it costs us speed. These new techniques are closing that gap, giving us near-perfect results in a tiny fraction of the time. And all of this pushes us to ask a really fundamental question about the AI we're building. As we keep racing toward faster and faster models, what are the trade-offs between perfection and performance that we, as the users and the developers, are willing to make?